5. 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. All a tau is a percentage of time, basically 20% of the time. It's a time constant. It's the time it takes to reach steady state divided by 5. That's all it is. So around 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. Now at 5 tau, where am I? 10 amps. I'm up here. We said at the first time constant, I was at 6.32 amps. So if we say this is 5, 1 amp, 2 amps, 3 amps, 4 amps. Quick.
Alright, back up for lunch break, boys.
Yeah.
We're that class now?
Cool, guys. It's too cold to open the window.
We're not plumbers. The plumbers actually have farting competitions in the classroom, you know, and it's like they're proud of it.
They like keep a score on the board.
You gotta stay.
Biggest part.
I'm gonna be honest. Dustin smoked out earlier, and then I just hit a silent one, but then I had a second one coming, so I kind of forced it, and that's why that's how that happened.
It's fine. We're above that. Oh, we're above that level.
This style of chair doesn't help the cause. Like,
It's got a hole in it.
will they really get loud?
First time constant, roughly there.
Hey, so is this cow guy a person or not?
Yeah. Awesome.
Was Tao a guy, or they just came up with this word?
So what was the next one? So this was 0.632. So the first time constant.
8.65 is
The second tau, the current in the second time constant was
The remainder of the 10.
6.32 plus 0.632 times the remaining of 3.68. So I'll kind of write it out like this, just so you can see a pattern. Third one. Well, it's going to be whatever was remaining at that point. This was 6.32 amps. This was we said 6.5 for the second one. So there. Right. So initially, the first one, well, that's pretty steep, eh? Fast increase. Why? That's a good question. 3-letter word, why? Why is it so steep at the beginning?
Because of what's the percentage?
Why is the current so high?
Percentage of the higher
Less resistance.
But wasn't it the current that's opposing it?
It's a fast change, right? It's a really fast change, right there. Because we have so much left, that it's the inductor. The inductor is blocking, but then it quickly subsides its pressure against the source quickly. So, but then when there's only a certain amount left, it doesn't have much to change in the next time constant. So the opposition of voltage across the inductor is less. So it lessens and lessens and lessens until it allows the full current to go. But how fast it changes, the counter EMF changes just as fast as the rate of change of current. So they can't really see this unless you put a big resistance in and watch the ammeter increasing very slowly over time. You know, if you had a huge resistance, very small current, you could actually watch that happen. Okay, so what about the next one? What's remaining? 8.65, so the remaining amount,
1.35.
so I'll do the remaining amount here. So the remaining amounts will be in this column here, okay, for each one. So what was remaining initially? When we first closed the circuit?
So it's 4 for 6.
10 amps was remaining. From 0 to 10, we had, how far did we have to go? We had to go all the way to 10. So the remaining amount was 10 amps. So then after the first time, at the beginning of the second time constant, we had 3.68 amps remaining. Right? And now 8.65 at the third time constant, it's 1.35. Right? I don't know if these numbers are accurate. You'll get roughly the right answer. So I'm going to say, okay, I'm going to say the remaining amount of 8.65 is where we are. We're there. We're going to say how much we're going to add to that. We're going to add 0.632 times the remaining amount, 1.35 amps. And then we get another number. Anybody? Third time constant.
0.85. 9.50.
9.5? Okay, 9.5. There. So we're looking at 9.5. What?
9.5.
No, it's 5032.
Okay, 50. Okay, so 4 tau equals, we had 9.50, so we still have that, so we're going to add that to that. 0.632 times the remaining, I'd say half an amp, right?
Just
Let's see what's happening here, right?
9.93.
Don't do that. You're not going to write stuff down and you're just like guessing. What's that?
How do you get to 0.5?
That's your measure.
Oh, 10 minus. So this one was 10 minus 0. This one was 10 minus 8.65.
Okay.
that's where he screwed up.
Sorry, not 8.6, 6.32.
9.8.
10 minus 8.65 was this one. This is where we started. So we started, so we had 3.68, 1.35, and then now we've got 10 minus 9.50 is 0.5 amps, right? And then, so if you add 63.2% of half an amp to the already existing 9.5 amps, a little bit more, how much do we have now?
9.816.
Okay, let's go 9.82, throw that in there. 9.82, so 10 minus 9.82 gives me 0.18 an amp left. And we're going to call that good. Basically, 5 tau is 9.82 amps plus 0.632 times 0.18 of an amp, and we're left with 9.93 amps. So, at that point, we do not call it 9.93 amps. At the 5th tau, or the 5th time constant, at the end of the 5th time constant, we call it 10 amps.
So
Always.
the taus don't have a specific
Always.
length, right? They just represent whatever you're measuring, broken down into 5, right?
That's it.
Okay.
Yeah. So what you're measuring is the increment of increase over 5 equal components of time.
So they could be 2 seconds and 1 second, whether it's 10 seconds.
We don't know the length of time right now.
Okay.
There's another.
graph then, right?
What's that?
You can draw your little graph.
Yep, yep. So 9.5, then we had 9.82 is the next one. This 4th right here is somewhere there. So you can see that's what you have. And now we call that 10.
That's gonna be a lot.
Basically, we call that 10. What about the other way? Say I open the switch. Okay, so in this case, let's get rid of this. say that I had in the circuit 10 amps flowing already. So we're going to carry on with this and say what would happen if I open the switch. So now we're running along, all happy here at 10 amps. And now I'm going to open the switch right here. So we've got this current here at 10 amps. So at this point in time, I start my time, right? So I'm going 10 amps, 10 amps, 10 amps. It's a DC circuit. So as you can see, oh, here's a good one. While we increased that current, what was happening to the counter EMF, the voltage induced into the inductor? The rate of change of current was less, so the counter EMF was less. So in proportion, maximum right away, blocking all the current, and then it gives up, right? And it's in proportion with the increasing current, the counter EMF is also decreasing across the inductor. So at the final stage, when you have maximum current flow, steady state current, maximum current flow, then you're going to have, let's say we had 120 volts across the circuit. We're going to have a voltage drop across the resistor. When the current has reached its steady state value, we're going to have a maximum voltage drop across the resistor, which is 120 volts. So if I was able to break this inductor apart without its resistance, right, because this is a practical inductor with resistance in it, if I could break it, say this is the inductor part and this is the resistor part, can't do that, right? How do you do that? The resistance is part of it. So if you could, what is happening inside is you have 0 volts blocking or opposing the source. So you have 0 volts of opposition from the inductor part and 120 across any resistant part. Basically it. If you had a pure inductor and a resistor in series, if this was not part of it, you would be able to measure this. It would be 0. Once it reaches steady state, it offers no opposition. Only offers opposition to the voltage when the current is changing. So when the current's not changing, no opposition. So that's just got to remember that. Yeah.
So, I'm actually maybe this is but the second you turn that on, are the values then switch? There's a 0 volt drop across the resistor, and then the induction is resisting all of the voltage?
Yes.
Okay, that's like that very first second of the...
Yeah, the instant,
Yeah, nice.
right here, switch is closed here.
This whole process is like the voltage value transitioning from induction to the resistance?
Yes, and it gradually becomes more across the resistor, yes. So then you open the switch. Now if I open the switch, the instant I open the switch, it wants to keep that current going. It's opposing the change to break the circuit. If it opposes the change to break the circuit, I'm going to get all kinds of arcing at this switch. Huge arcing in a DC circuit.
120 volts.
Arcing is current, right?
Yes.
So across that break, you're actually going to have a high induced voltage across the inductor, which is going to try to keep that current going in this direction here. And it wants to keep it going. So as soon as you break that circuit, this is going to develop an aiding voltage to the source. So you'd actually see a high voltage across there, not the source, but a high voltage across the contacts. To be able to conduct through air, it has to be really high voltage, right? So we'll deal with that just after we do this. Okay, so we've got a opening of the switch, and what we're going to see is a pattern like this. So this is like the tank above the trough that you're filling is draining. So the instant you're draining, it's draining at a maximum rate. And this, by the way, this is a universal time constant. This works for every kind of type of physics everywhere, is universal time constants. So instantly it's draining fast, and then it slows down. This curve might not be as steep as I've drawn it, but if we plot the numbers, we're going to get that same pattern, so we don't have to erase it or anything. We got 1, 2, 3 to 10, right? 5. Boom, 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 boom. Okay? The instant we open the switch, right now it's at 10 amps. So one time constant, so if that's where we open the switch, we have to say one time constant away from that. Before it reaches 0 amps. So 0 amps is our target now. Right? We want it to be off. We don't want any current. So we're aiming for 0. Now that's a good number to aim for, right? You know, he who expects nothing will not be disappointed.
Just like me.
You know, I thought this would be a better crowd. All right, 1 tau, 2 tau. 4 tau, 5 tau. Regardless of what we get at 5 tau, we're going to call it 0 amps. Okay, so let's get rid of all this. Easy way to do it is to say, okay, 1 minus 0.632 is what number?
6.32.
Yeah.
1 minus 0.632 is what number? 0.368. Okay, 0.368. So if you take 0.368 times the remaining value, it's actually easier to do a falling current than it is to do a rising current, because with the rising current you have to add to what you had before. Well, if you're aiming for 0, what you have remaining is always the number remaining, right? It makes it easier. So if you say, okay, 1 tau, 2 tau, 3 tau, 4 tau, 5 tau, and we say equals 0.368 times 10 amps
We do 6.32.
is what? So I am at the 3.68 amp level after one time constant. Roughly there. Right? Where did we start? We started up here. Right? So we're falling rapidly. It's sort of a pattern. It increases rapidly on closing the switch, falls rapidly on opening the switch. But there's something blocking it, right? There's something trying to keep the current going. It's not going right to 0 right away. When I open the switch in a DC circuit you've learned of before, is that it's instantly off, right? The inductance of the inductor is keeping it from going completely to 0. It's opposing that change. Okay, so then we go 0.368 times 3.68 amps. What do you got?
1.35 for
1.35? So small.
It's just so like the difference between the 60%.
Well,
62%.
Point five?
0.5? Is it?
Yeah, 0.49.
0.49? What do you guys get?
0.498.
Oh,
Say the right number.
okay, 498. Let's do it that way. Okay. So I'm going to go down to the half amp level at the third time constant. I'm like between 0 and 1 here, so I'll just plot that. And then we go 0.368 times 0.498 amps, or 496, or whatever you had.
0.183.
Very small, very small. Our goal is 0, right? 0.183, okay, so 0.2 roughly, I've got to be somewhere about a fifth of the way off of 0. And I'm going to call the fifth one 0, but what do we get just to...
0.067.
Sorry, say again.
0.067.
Okay, that's reasonable.
How do you get 1.83?
0.183?
Well, I understand part of it, I just don't.
I'm only going on your guys' numbers. Somebody want to check it? It looks pretty good, you know.
Close, close.
Okay, we'll call that 0 amps. So after 5 time constants, we've reached our goal. We're heading for 0, 5, we're at 0. Okay? So this is the graph that you get for a current in a through an inductor with resistance. So if you have resistance and inductance in a circuit, the value by which this falls, or the speed at which this falls, is based on the ratio of the inductance to the resistance. The amount of inductance to resistance. The amount of henries per ohm, you could say. So we're looking at the inductor. How much inductance based on the what? Number of turns? What else?
Permeability.
Permeability?
Amps.
Not amps.
Oh.
Area, cross-sectional area, length of the core, all those core properties, and the number of turns of the coil. That's what the inductor is. So based on how much inductance the circuit has compared with its resistance, we'll say how fast that will happen. The more inductance, let's see, more inductance, it's T equals L over R. So one time constant equals L divided by R. Let's find that so you guys know where I am. I don't even know where I am. Okay. So the initial rate of rise, this is what I was saying, if you could draw this little bit here, where the initial rate of rise, and continue it to your goal of 10, it would increase at this rate. At the second point, it's increasing at this rate. So you can see that the rate of increase is slowing. That's really what's happening. All those little rates of increase. And when we get to sine waves, this afternoon, I'm gonna draw, like, showing you that it's a change. It's how fast something is changing is the whole key to this. It's how quickly something's changing, in this case, current. Okay, so this is your formula. So if I had, in 100 millihenries, let's do a circuit here. I like that number. Let's say 12 ohms, 120 volts. There's my ammeter. And if the inductance was 100 millihenries, how many henries is that?
0.1.
So it's also known as 0.1 Henry, or 1/10 of a Henry. Okay, same thing. Okay, so if I take that to the amount of resistance in the circuit, which is 12 ohms, in that circuit, it's what? 0.1 to 12.
0.0083.
And this works out, Henry per ohm works out to seconds. Okay, so just magically, if I show you physics units, and we could cancel them and make them all turn into seconds. Anyway, so, yes, what do you got? 120th is what?
0.083.
0.083 repeating seconds, right? That's one time constant. How long will it take for the current in that circuit, if this was that circuit, reaching 10 amps, how long would it take in time, change in time,
5 of those.
the whole way from 0 to that point will be 5 of those time constants. So you could say, okay, the ratio of one time constant, a little tau, that's why I drew it so tiny, so we know it's a tau, and it's not a time, the change in time would be 5 of those, 5 tau, which is 5 times 0.0083 second. Some guys forget to times it by 5. Just so you know where one of the pitfalls is. What do we got?
0.0415.
Okay. 4/100ths of a second, roughly. So it's pretty fast. Okay, what if I changed this to a larger inductance? We'll do the same thing, so that's my answer for that one. How long will it take to reach, oh, by the way, how long will it take to reach 0 when I open the switch?
Same time.
Same amount of time. Same amount of time because we haven't changed the circuit. Just a different graph that's dropping drastically, but 5 of those would be the same amount of time.
If you increased it, your time would increase.
So what is this time based on? From this point, right there where I open the switch, to when it drops to 0, that equals 5 time constants. This one equals 5 time constants.
Your answer would,
It's really easy, actually.
when you increase your
Yep.
enemies, it just goes up.
Okay, so
What are we gonna do the same as this?
change this to
No, okay.
1 Henry. Is it quicker or slower? It should be,
Same.
is it a larger number of seconds or a smaller number of seconds?
It's
Yeah.
larger.
So if I increase the inductance, then it takes longer to reach 0. Why? Because that inductor now has more power to counteract what the change is. More inductance, more turns, more muscle, you could say. More inductance is like more muscle in the circuit. Less inductance means, a little bit, right? So you think about it that way, more inductance. You could draw the formula and just say, if this goes up, time goes up. What if I have less resistance in the circuit? Yeah, less resistance would also, because the current would be changing more rapidly because there's more current to go, more current remaining. It would just like be lots of current. So what if I had more resistance? Yeah, it would actually have less time. Less time. So anyway, you can play with the numbers. And this was 1/12 of a second. I don't know what that is. It's 1 divided by 12, so times 5 would be 5/12ths of a second. It's not quite a half a second, right? So
Like 0.41.
yeah, something like that, or 1/6666 or something. Yeah. But if you think about it in fractions, it actually makes sense. It's 1/120th of a second per time constant, or because that's 1/120th, or 1/12th. 1/12th of a second is bigger than 1/120th of a second, which is way quicker. Right? All right. Any questions?
Yes.
Yeah.
Why does more resistance equal less time?
Okay, more resistance would be less time. I always have to look at this because the formula says so. So if you have more resistance in the circuit, if there's like more resistance, 24 ohms. 24 ohms means I have 5 amps to reach, right? Instead of 10. So 5 amps to reach, it's the ratio of what kind of change of current the resistance is going to allow in the circuit compared with the amount of inductance that will oppose that change. It's the best way I can describe it. It's all I got right now, okay? Because if you put you know how to use formulas in this way, do you?
Yeah.
Write it down, mathematically it makes sense. They're inversely proportional to the resistance of the circuit. It's this ratio, L divided by R. Okay, I'm going to shoot down to, yeah, go ahead.
Well, what was the first graph, what we got 0.632 where? And the second one we got 0.328 from where?
Okay, hang on a second. this little exponent button is on your calculator. It's a universal time constant function calculated already for you in your calculator if you can properly use it. Okay? So on my calculator, see here.
See it.
Oh my god, no.
Is that?
It's right on the little half button. I got the same one. Watch your mouth. What? It's raise your math button? I think it's not. Yeah, you gotta turn second function that shit.
Got it.
Second
But you could be wrong.
Could be wrong. That's why I allowed that safety and said that, just in case you're wrong. It says I'm stupid.
The X.
Do it again. Yeah, worse than that.
So, what if you did?
Tripping on.
What would you do there? I just put it in 5.
Whoa.
Yeah, sure.
Whoa.
Okay,
That is great.
so where is it?
On the end button.
That's full K.
Second function.
Second function.
Yeah.
Okay,
Quick scroll for you.
so if you go, second function, e to the x.
Okay.
Yeah.
Yes.
Okay, there you go, you have that. Now, you do that, and it says on page, because I can't go back and forth now, I only have one screen, so page 74 has the graph.
I'm glad I bought it.
And then you go negative, so let me go, just back up a little bit here so you can see the whole calculator.
That is great.
I guess
That is pretty sharp.
Got some mad
Glare
glare.
here.
Yeah, it's sharp. It's sharp.
Bit of a glare there.
Got that.
Yeah, that's fine.
Oh, right there.
Okay, so you go negative, negative, the little negative button, not the minus, but the negative.
Doesn't say
You go to the-
negative.
Because that was screwed up. And then you go 1 equals.
0.367879441.
So there's your 0.368. If I want the second time constant, so multiply that by 10, you got 3.68 amps, right? Okay, what if I want the fourth time constant? I'm going to go
No way.
second function, exponent, -4. It's going to be
Slow down.
0.183 times that. What did we have for the fourth one? 1.183. Well, 0.0183 times 10 amps.
Yeah, I didn't
was
do it right.
1.83.
How did my calculator do that?
Go again?
Wasn't our tau calculated by our inductance and our?
-4.
This is the time.
Is this something
This,
called?
or not the time.
Is this
No,
like
no,
an
this
electrician
this
calculator or
part was
something?
the time. This was the time it took.
Okay.
This wasn't the rate it goes. All you're doing is saying, I'm going from here to here and 5 time unknown segments of time equal segments of time. And we're calling time constants. Right? Let's go to the fifth time constant.
Let's do it.
To infinity. Exponent -5 times 10s.
Oh, you got time?
Well, just to get this 0.067, so you guys were right. So I can verify all that based on the calculators. Anyone know about this already?
No, this is all new.
What is going on?
Okay,
Mind blown.
now,
But then,
what about the other way? What about the other way? So
Don't you
you-
Positive.
you have, this one you go 1 minus e to the negative tau, whatever the time constant is,
not.
times the steady state current. Will give you where you are in whatever time constant, little tau there. This one, you go e to the negative tau times the steady state current. This one's 1 minus, and this one is just plain old e to the negative time constant. You gotta do the negative after the exponent. See, so when it did that, I went, if you can sort of see it, I went to the fifth time constant here. Went e, second function, exponent, -5, and that's what it came up with. And then I times it by whatever current was the full value of current in the circuit.
Do you still put in your negative function or your negative time?
So let's look at what it is after 5 time constants the other way. You go 1 minus exponent -5 bracket times 10. 9.93.
Ooh.
So there you go. So wherever you want to go, this one you go 1 minus for the increasing, and this one you just go plain old exponent without the 1 minus.
That's too much.
So if I like
It's too much work.
50 volts, you just times by 50. And there you go.
Volts, right now we're doing current.
Or sorry, yeah.
Yeah, 50 amps, yeah, then you would use 50 amps as your value times it by steady state value. If I had 1.2 ohms in here, I'd have 50 amps, yeah, so, yeah. Or 100 amps. 100 amps. Try it out, it's really cool. I don't know how to do it on other calculators. I've tried to do it on the Texas Instruments one, wherever that is.
Try it on mine.
I don't know how to do it on yours. You have to figure out yours with your manual or whatever.
The Texas Instrument one is just on the LT button.
Below the log button or something.
It's below the log button.
This is a different Texas.
You have the same one as me?
Oh, here
Why
it
is
is.
it-
Second
Is
function.
that ratio like applied to
But if you
different
don't, the
other
problem is it doesn't type
functions?
Oh,
this.
yeah.
Why is it like
No,
in this calculator?
Okay, so on its way there, it's not going to be instantly 50 amps. It's going to increase and gradually, but more rapidly right away, and then going to taper off, and then it's going to be full value. So it'd be like this. So the first time constant, you'd be 0.632 times 50, right? So I don't know, 30 something, right? So 30 something amps. So you're already at 30, and then so 2, 3, and 4. So if you use this on your calculator,
Makes life so much easier.
is that what you guys did?
It does.
Yeah, okay, good. So 1 minus exponent -4. And if you can't do this on your calculator, you gotta do it the long way and just do it this way.
Or you can buy a calculator.
There it is.
We did that.
Sharps kill.
So practice, practice, practice is the whole key. And then how long will it be after 4 time constants? So what do I need to solve first?
You gotta get your henries into, your millihenries into henries, which is 0.3.
I use this L over R formula.
Yeah, that one. Top to
And I was
top.
thinking about it, the larger the resistance, the less of a current change that it would cause, so then it would go quicker. It's kind of like that's kind of that reason. How equals L over R
Or it's always negative, whatever.
equals 0.3. Change it to henries. That's
Yeah.
important.
You gotta divide that by your ohms,
Oh, that's very wrong.
which is equal
So
to
we're looking at 3/20ths.
0.15.
Yeah,
Then you have to times it by
0.15, you're right.
Yeah, then you have to times that by 4 constants, so.
Seconds, those are seconds. Remember the time base in the SI system, seconds is the time, so all the formulas are gonna work out to seconds. As long as you put in henries and not millihenries, it'll work out right. And then you go change in time, fourth is 0.15 seconds times 4.
0.6.
Because you're only counting it at the fourth time constant, right? So 0.6 seconds.
Crazy.
Is that right?
Yeah, that's right.
Okay.
My multiple choice was right, Ron. Always
there
pick
you go.
C. Always pick C. That's the key. Have a go, sir.
Easy? Just get your brain around it.
Just get it around it.
Any more questions? Move on to the next thought here.
Can you do one more?
Next question? Let's look at maybe one of the examples. They have one? No, they don't.
No, they don't.
Okay, they don't have an example. Okay, let's, okay, what would it be when the switch opens? A value of current at third time constant when switch open. There you go.
Same resistance and.
Yeah.
2.4.
I found nothing, so I found a house.
Your worksheets should have questions like this inside the worksheets package. Don't forget about that.
Was that what it was?
Value of current at third time constant when the switch is open. Yeah, I was reading it while I was saying this.
Third TC.
When the switch is open.
So switching four to eight?
So we're going to open the switch and then allow for three time constants and freeze it. What value of current is that, right at that point? It's just an exercise in understanding how to calculate this stuff.
2. Yeah.
Like 2.48?
Yes.
So what do? E to the negative 3 so the current at 3 tau equals E to the negative 3 times 50, yeah. Always times it by the steady state value.
2.489, 353, 114.
So it would be more like
2.4?
0.49, no, 0.0498.
It's all
Anyway, I'll
about
do it on my calculator. Negative 49.
error.
2.489, yeah, so 2.49, right? Pretty fast. Well, not maybe not, but however long that takes. Okay, how long after the third time constant?
0.457.
0.45 seconds, yeah, because you got the one time constant already for the one question, which was 0.15, so it's just how many times are you multiplying that by? Just third is, yeah, 0.15 times 3, 0.15 times 2, 0.15 times 5, this would be the total time.
0.15.
Anyway, I gotta move on to this energy in an inductor thing, so hopefully that, if you guys have any more questions, let me know. Thought I did a real bang up job. Getting to lunch. Okay. If an inductor has no resistance, think about this, no resistance, no opposition to flow in a molecular way because of the material it's made out of, so resistant, we're talking resistance. Will it dissipate any heat, any energy, or anything? No way. Because it would be I squared R. I squared 0. Get 0 again. Every time I multiply by 0. Zero resistance, I keep getting zero. I think there's something wrong with my calculator. Let's see, we have 1,000 amps. 1,000 amps squared times zero. I keep getting zero. There's something wrong with my calculator. So it doesn't have any resistance, it does not dissipate any energy, that's the key. If there's no resistance, so that if it does have resistance, whatever amount it has, small amount, what is the rate of energy dissipation in this circuit we drew here? Once we reach steady state, what is the rate? How do we calculate it? Yeah, I squared R, yeah. So if we say, okay, what is basically the power dissipated out of that resistor is how fast it's using the energy, right? That's a rate of heat. So power is a rate, speed. So at what speed is it dissipating the energy?
I thought it's 7.5, whatever your thing is.
So I squared R
I didn't do that.
equals
I definitely did a different way.
50 amps squared times 2 ohms. 5 times 5 is 25, so 2,500 times 2, it should be 5,000 watts.
I was doing the story.
5,000 joules every second. That's how fast that heat is being dissipated. That would be a really smoking hot circuit, right? So it's probably a heater. It's a 5 kilowatt heater. There it is. For some reason it has a coil in it. I don't know why. Anyway.
Do they even make a 5,000 kilowatt heater? Well, base board heater.
No.
They usually
I think they're usually in the bigger units with the fans.
like the big, yeah, it's like
Or the
this
unit
one,
heaters.
2,000.
So there's your inductor. There's your fan. Yeah?
Yeah.
Maybe. Anyway, so even though the inductor doesn't dissipate energy, it does take energy from the source to create a magnetic field. Does that make sense?
Yes.
You can't get the magnetic field unless energy did it, right? You can't take it from nothing. So energy has to be stored in the form of a magnetic field. So it's like I'm just going to take that energy and I'm going to just store it there, magnetic field. Once that's established, you don't need any more energy for that. You just need it a little bit. And you can't measure it because it happens so quick. So it's like it didn't happen. It's kind of like that. Trust me, this is the way you got to understand this. So if we say, okay, even though it didn't dissipate any energy, it takes energy to create the magnetic field, to produce those lines of force, and they're there. They're set up. How many ever? What determines the amount of magnetism created is the amp turns. Right? Magnetomotive force is the amp turns. Right? Okay, yeah. All right. Anyway, once we increase this voltage across, once the current reaches steady state, the current across the resistor is at maximum. We have maximum voltage drop across the resistor, and the inductor doesn't have to supply any energy to the circuit, or sorry, voltage drop to the circuit. So its only thing limiting it at steady state, I'll go back to this one, is in this case 10 amps, in that case 50 amps, right? Our example there, 50 amps. The only thing limiting it is the resistor in the circuit. So the inductor is not offering any kind of forces or electromotive forces to oppose the source anymore. But inside the inductor, this part here, the energy must still be in the inductor somewhere. We didn't get rid of it. Stored it, magnetic field, and now it's still there. In fact, it increased the magnetic field, right? Because more current, more magnetic field, but it's not producing any voltage because the current is not doing what?
Changing.
It's not changing. So but the field is set up in full, more than it was even when it was changing. So once that field is there, there's a certain amount of energy stored in that inductor, and when you open the circuit, you're going to see arcing, where does that arcing come from when you open the switch? If the source is disconnected and you open the switch, the energy is stored in that inductor, and sometimes that's huge energy. Your spark plugs, your car, huge energy, right? That's what's causing it. It's stored in a coil, in an inductor, right? So that's how you calculate it here. You say, okay, well, it's based on current, so the amount of turns is going to intensify that, so it must be the inductance of the inductor times I squared, and then we're just going to times it by 0.5. Because it's like an average of all that, right? It's like a point, it's like an average. So energy in W is W, which is in joules. It's the amount of energy. It's like, it's not the speed at which the energy was absorbed into the magnetic field, it's how much is there. It's like you're getting charged by hydro for so many kilowatt hours. This is just another form of it, joules, which is like a watt second. Watts times seconds would be joules.
Would it just be 1250 for the answer?
I don't know what the answer is. So for this one, okay.
Yeah.
So half of 0.3 times 50 squared. So let's
I did that.
do it over here. Get rid of this guy. This is the easy one. So I'll erase it.
335 actually. I was just kidding on that first
They
answer.
use W. Why do they use W?
Work.
Work, which is energy, same thing, only one is, they could be different forms of energy, so they call it work, equals 0.5 Li squared, 0.5, 0.3 henries. Taking this circuit here, times 50 amps squared. Okay, so I've got 2,500 times 0.3.
375.
375 watts, or no, so 375 joules. There you go.
You do math problems for fun,
No,
You were about to say yes.
Not anymore.
I just didn't want you to think.
My wife made me stop. I used to do.
Okay, easy? That's just a main thought, but this thought of energy stored in a magnetic field, it makes sense. You have to store it, it's still there. Now I open the circuit, and what happens is that energy now has to come back to the source. And sometimes, in order to do that, it will arc across a switch, and part of the energy will be dissipated in destroying the switch, right? It's always good. And then the other part will go back to the source. So it takes it back. Yeah.
So we say that stored energy in a magnetic field.
Yes.
How long is it? Because it can't just be the same amount of energy making the same amount of lines of flux. It's got to be dissipating. I mean, you're losing energy keeping those lines of flux together. Does it take energy to keep that? Like,
if there's no resistance in the inductor, right? Okay, look at this circuit. For however long this took, let's say 5 time constants. In those 5 time constants, which was 0.6 of a second, or no, sorry, 0.75, 3/4 of a second, because there's 5 of them, right? In the 3/4 of a second, we've used 375 joules from the source to produce the magnetic field. In that 3/4 of a second. So just like, boom, 1,000, there you go. There's 3/4 of a second. It took to use, what rate was that? Well, you could say that it was how many joules per second. We're not going to do this. He's asked the question. So joules per 0.75 seconds is how many watts would it have been average, the average watts that it would develop?
500.
Because it would change rate, the average rate of energy. So it's 500. So it had an average of a rate of 500 watts for 3/4 of a second and then nothing. So how much energy was that? 375 joules of energy. You could say, okay, well, how much energy did the resistor average have in 3/4 of a second at steady state? Right? If this guy is now at 0 watts, because he's not, the current is not, the magnetic field is already there. You don't need to, you can't develop anymore. Once the current is flowing and not changing, it's now that magnetic field is set up and everything's happy, and now it has to go through the resistor, and all this heat is through the resistor, but that magnetic field is not going to do a bloody thing anymore. So we're going to have how much in 3/4 of a second. So if this is work equals power over time, and all we have to do is say 5,000 watts divided by 0.75 seconds, in the same amount of time, if we're already at steady state. This one has 0 joules in that 3/4 of a second. How much is being dissipated in the resistor? You gotta do the math, right? What is it?
3,750. That's what I timed it.
Other way around.
One job.
6,000.
That devil.
6,066.66666667.
6,666.67 joules. There you go. Is that right? Or is it more decimals?
You can divide.
Yeah, you're right. Anyway, so just getting the idea now that
Just adding
energy is, we're just talking about the amount of energy that's stored there, not how fast it took to get there. It took 5 time constants to get there, and now forevermore, 0 joules of energy are required to keep that magnetic field going because it's already there. It's like you already have the pressure in the compressor. You don't need to build up the pressure anymore. It's sitting there fully compressed. Right? It's kind of like that. I don't know. I don't know what else. What about if we collapse the magnetic field really quickly? Faster it takes. What if you collapse the magnetic field? What's happening to the induced voltage in the inductor?
process.
As it's collapsing,
Yeah.
it's just getting larger.
It starts out full, right? Okay. So I'm going to just go into this one. In a practical inductor, which means what?
Inductor with resistance in it?
It has resistance in it. So if you, it says if you put your fingers inside an elastic band, stretch out the elastic band, there's energy, and if you slowly allow that to contract again, it slowly releases that energy back into your hand. It's kind of like that with the magnetic field. So the magnetic field, if it's quicker, then it quickly releases that energy. What does it say? Sometimes it changes the energy into sound as you hear it go snap. And sometimes, okay, as it flies across the room. So you can use the energy for something on an elastic band. I don't have any elastic bands, or I'll look for people that are sleeping and do that.
Yeah, I'll fall asleep once or twice.
Stop asleep.
It says, consider the following, right? You want to build an eye, I can't do that, but consider the following.
Pretty close.
Hey, Bill and I talking about that stupid pressure thing too. Notice how the hole didn't touch.
Figure 3, what's figure 3? So first of all, current has reached 8 amps, and they're considering the switch to have an open resistance of air of 500,000 ohms. They're just saying, okay, let's make it, we don't know what it is. They're saying, let's make it a big value of resistance. Okay, let's try that. Where's figure 3? Where is figure 3?
It's like back 2 pages.
15 ohms. Okay, so we're back to the 15 ohms, and there's your switch. And they're saying the open switch there has a resistance of 500,000 ohms. Okay? I hate it when I do this. At the instant the switch is open, the resistance is 500,000 ohms, and the field around the inductor tries to do what? It tries to keep that 8 amps going, right? So the field collapses at a really fast rate. It's like the field around the inductor, around the coil, or whatever it is collapsing really quickly. So when that happens, there's a rapid change in field, change in relative motion between conductor and field, like really fast, right? So what happens when it happens really fast like that is that it induces a high voltage. And here it is here. If you have 8 amps flowing and it tries to keep that 8 amps going and you multiply it by the resistance of air, you're going to have 4 megavolts of voltage across that switch. Where did the energy come from? Stored in the magnetic field of the inductor. It's just a form of energy, right? It's there. It's real. Okay? Even though you can't see it, smell it, taste it.
Can you
Taste it, you shock yourself.
Well, you can feel it if you touch it. I don't know. So the high induced voltage, it says the ignition systems are good for that. Good for providing voltages up to 80,000 volts in your ignition system of your car. Anyone work on cars? A couple people?
After I crashed,
You get an ouch from your ignition system at any time in the past? No? Okay.
that'd be a big time out. Clever guys.
So these are voltage spikes. So what happens? In a DC circuit, this inductor with some resistance, and of course inductance based on the number of turns, etc., is, and this 500,000 ohms, if we had 8 amps, 15 ohms, 8 amps, if this was a really big value of inductance, it would oppose that change and it would try to keep this going. So something with many turns, like, would be a high inductance, right? Something high. So let's say 2 Henrys. 2 Henrys, I don't know.
Is that a high inductance?
It is, yeah, it's pretty high. It's usually in millihenries. 15 ohms. So there's more L than there is R. The ratio is huge, right? How long would this take? Quite a while. It would take a while to dissipate that energy, right? Because there's more inductance than there is resistance. Well, not that much time. 2/15 of a second times 5, right? So, 10/15. So here we go. When we open that switch, there's resistance there. And this voltage here, when it's, let's say it's 120 volts, I think they said. It's doing this. What you get is a high current inducing a voltage way higher than even the source. It aids the source. So when this switch opens, which direction is the current going before I open the switch? Okay, which is clockwise.
Yeah.
So what this inductor does is it tries to maintain that as a source and forces the voltage is going this way, it aids the source. It aids the source. So it doesn't matter what the source is in this case, it's all based on the level of current and I times R. So we say at the instant the switch is open, what do we have? I erased it, but we have maximum. If we were to draw the other graph, we would have maximum 8 amps in this circuit. Okay, we go 8 times 500,000 would be the voltage drop. That's what they're saying in that example. So 8 amps times 500,000, 4 megavolts. That's what they said. They don't know. They're just saying what if. If that's the case, Kirchhoff's voltage law, around any closed loop, the sum of all the voltage rises equal to voltage drops. Well, this is a voltage rise. This is a voltage rise. And this one is a voltage drop. What kind of voltage drop is there across the resistor here? 8 times 15, I times R there.
Just 120.
I guess, yeah, it would be. So we're dropping 120, right? Dropping 120, and then we have a voltage rise of, what's the difference between 4 megavolts? What do we have to have? Another source in there somewhere. We have to. 120 is not enough because we're already balanced here. So what's the inductor producing? 4 megavolts. To balance it out. This is a source. This is a drop across the switch. The resistance of the air across the switch. What kind of energy, what kind of rate of heat is this? I squared times R. So what's the power, what's the heat rate? Rate
32 million?
of heat
Or 32 million
equals
watts?
I squared R. This R.
So,
32 million?
Yeah. 32 megavolt.
32 megawatts.
Yeah.
So do you see why switches are destroyed?
Yep.
So that's kind of the principle behind it.
like theoretically, it's a 120 volt circuit, and you put like a 2 Henry inductor in it, you could have like 4 million volt. Like, where does it get that much? Like, there was whole conversations based on that. I don't understand where it can get that much. You can't create the energy, right? There's no energy can't be created or destroyed.
Right.
So where is it like just where does it get that much power?
Magnetic field. You had, in this one, how many joules of energy were stored in that inductor? What was that? 2 Henrys Li squared, 0.5 Li squared. How many joules is this one? This is bigger. 64? Oh.
64.
Oh, it's only 64. Okay. Anyway, this is 64 joules. So this one has 64 joules of energy. Is that a lot?
I don't,
No.
probably not.
No?
I don't think so.
No, maybe not. Anyway, it's for a very short time. For a very short time, it produces a very high voltage, and it's based on the fact that this has so many turns. So your ignition system in your car has lots and lots of turns to produce a very high voltage, and when the points are open, right, or whatever, the arcing across the gap will cause a spark. Here's an example of that actually at the end here. Oh, by the way, how do they get around that? They throw a field discharge resistor. And a field discharge resistor is a special resistor that's really, really high on low voltages, but when subjected to higher voltages, it allows the current to flow through it. So normally this would block, but because the voltage is so high, it actually sends it through the resistor's path. They're called non-linear resistors.
It's like a safety thing? Like
Yeah.
67.
FDR, field discharge resistor. You'll see it in like level 3 a lot. FDR, what's that? A field discharge resistor. It takes the energy and protects the equipment. That's what it does. Also, freewheeling diode, same thing. It takes the path of the diode. Once this becomes negative here instead of positive, it becomes a source, and this becomes a source. So it's forward biasing the diode and protecting this switch from this exact thing. This would destroy the switch. Hitting the contacts. Yeah. Yeah. Anyway, we've done some math on this already. So here, mutual induction. Here's something. Let me just finish this one before you guys take your break, because we need to finish a thought here. Mutual induction, because of the counter EMF when the current is changing, while that current is expanding, or that magnetic field is expanding around this, or through this core, if there's another coil next to it, but not electrically connected, we saw him do that in the video yesterday. If you put the loop of wire over top of it, it induced voltage, and they saw he had his galvanometer hooked up to a little laser so that you could see it on the wall. That was so that everyone could see it, right? He didn't have one of these, so you could put it, put it there. So if the galvanometer went one way, then it went the other way when the current fell. Right? It's the same thing. So when the flux is changing around this one, it's also cutting the conductors of the next one. Only when it's moving though. Once it's steady, there's nothing. So you can induce a voltage into this winding through the air. Right?
Transformers.
It will be mutual induction, and we'll get into that later. But the same principle with inductors is the same principle for transformers. It's mutual induction, meaning there's a second winding, so they mutually share the same field. Okay, and then there's I think there's a formula for that, MI squared or something. Mutual inductance. Low reluctance core would be better than an air core. What do you say?
I would say.
So you got a bunch of fringing through the air here, low permeability, very low. What happens when I increase the permeability of an inductor? It gets higher inductance. So higher inductance means more muscle, more flux, more everything. Then you're going to induce a higher voltage into this winding. That's a transformer. So if you use AC. DC won't work. The only time DC will work to induce a voltage into that other inductor over here, this is the source. If this was DC, and I had a switch, the only time is when I close the switch for the first 5 time constants. It's called a kick test. So it kicks the voltage into the next one, and you'll see that if you had a voltmeter across that, it would go, and then it would fall to 0. And then you open the switch, and it would go the other way. And though it's called an inductive kick test. Only transformers do not work on DC, but you can use them for certain applications for a very short, brief time.
Because that's when the current is changing.
Current is changing. Yeah. There you go. And there's to explain all that there. And then the other one is, instead of putting L in there, they say just change L to M and call it Henry's. Mutual inductance between the two. So it's not a new formula or anything. Okay, and then number of turns is a ratio. So you'll get into that in transformers. You have more turns in the secondary, you get a higher voltage out of it. More turns, higher voltage. Volts per turn. Here's your, how does this work?
Take your card.
There's somebody named Cam in the class who do that, so I can do that, but there isn't. Spark plug? Rotor? So what's happening here?
It's turning.
Yes. Okay. Is it AC or DC?
That's from a battery.
Okay, battery. Okay. So here's your kick test. Mutual induction is the principle that your ignition system works on. So you have current flowing. This is a positive, so it's actually flowing up to here. Negative, so if you want to follow it out of the negative, we could call that the negative. Let's just call that the negative. It doesn't matter. We're grounding the positive in this case, which you don't do in your car. I think Japanese models used to do that in chassis, where they grounded the positive instead of the negative. It doesn't really matter. They picked one, they chose the negative, because they all like conventional flow. But anyway, so let's say electrons are going through here, and then back down to the other terminal. Okay? What is causing that current?
Battery.
Battery? Yes. What is starting it? Key. Right there.
Ignition.
Okay? So what are you doing? You're causing flux to increase through the coil, right? So what happens then? You got distributor points here.
Looks like it closes at.
It's,
Is it mechanical? I think it is.
Looks like
Anyway, okay, so, and you've got a capacitor to stabilize that, but let's not get into that. Okay, now what's happening into the secondary? Well, the same flux that's expanding out of this one is in the same core, so it's expanding everywhere. So it's causing this higher voltage to happen here because there's more inductance in that one. And we know that L delta I over delta T, the more inductance, the more induced voltage. And that's what you get here. And so it goes to one spark plug, and then another spark plug, and another spark plug, and another spark plug, and basically it's
eventually one is gonna pop off.
yeah, well, you don't want, you need 4 in this one, unless you have 6 or 8.
Well,
Well, anyway,
just wants to read.
that's it.
this class would have.
So anyway, let's take a break. Yeah.